Hello, everyone. We are starting the Pearson text, section 11.3 to 11.4. In 11.3, we're going to be looking at the volume of pyramids and cones. And in 11.4, we're going to be looking at the volume of spheres and also actually the surface area of spheres, which we did not cover when we covered surface area of other three-dimensional figures. Okay, so we'll start off here with the volumes of pyramids and cones. And you'll notice here, if you look at these formulas, you notice the volume of a pyramid is 1/3 the product of the area of the base and the height of the pyramid. Okay, so if you notice, if you cover up the 1/3 there, what you'll get is area of base times height, which would have been the volume of a prism with the same base area as this pyramid. So basically, if you have a prism and you have a pyramid that has the same base area and the same height, the volume of the pyramid will be 1/3 that of the corresponding prism. Okay? Also, the volume of a cone is 1/3 the product of the area of the base and the height of the cone. And you know that the area of the base, of course, is going to be the area of the circle. And you'll notice the same is true here when you compare a cone to a cylinder. They have this, if they have the same base area and the same height, the cone will be 1/3 the volume of the corresponding cylinder. Okay? So we're going to look at some application problems here. Okay, what we have here is a pile of corn, and it's in a shape of a cone. Kyle's truck can haul 1 3/4 tons of corn per load. Okay, so first of all, you want to notice that the units that we're being given here is tons, and also load is also a unit of measurement as well. Okay, so his truck can haul 1.7 tons of corn per load. Okay, 1 cubic meter of corn weighs 1 ton. Okay, so now we have another unit of measurement here, a cubic meter. Okay, and of course a cubic meter is a measure of volume, and we're being told what it weighs. Finally, the question at hand is how many loads will Kyle haul to move this pile of corn? Okay, so we want to know how many loads he will haul to move this pile of corn. Now, you'll notice here that the information we're given, the diameter of the base here, 4 meters, okay? Because basically what you want to understand here is, if I kind of draw here, the shape here is that of a cone, right? So if you were to kind of redraw this to kind of help you visualize that this is a cone, there's your circular base, and the 4 meters is the diameter of that base, okay? And furthermore, the 1.5 meters is the height of the cone, okay? So what we can do is we can use this information. I think I'll lower the light here and see if that gives you a little better view. I'll use this information to be able to calculate the volume of the cone in cubic meters. Okay, also zoom in a little bit here. So we're going to look at the volume of the cone in cubic meters. So let's do that first. So basically we're starting out here with meters cubed, and ultimately we need to get to loads, okay? But they're telling us that we need to have a certain number of tons of corn per load, which means we have to convert the cubic meters that we get when we use the volume of the cone to tons first, and then convert tons to loads. Okay, so that's our plan. If we were to make a plan of what we're going to do here in steps, those are the steps, okay? So step 1, let's find the volume of the cone. Okay, so if we look back up here at the formula for volume of a cone, we have the volume of a cone is 1/3 the area of the base times the height. But the thing is, with a cone, the area of the base is always going to be a circle. So that pi r squared here is always going to be what you're going to substitute for area of the base. So I can just go ahead and I can just use this formula directly. The volume is 1/3 pi r squared times the height. Okay? So the volume equals 1/3 pi r squared times the height. Okay? So notice we're given the diameter here, and a common mistake students will make is they'll accidentally substitute the diameter for the radius. So you want to make sure that you recognize that the radius is actually going to be 2 meters. Okay, so we're going to say 2 squared here, and then the height is going to be 1.5 meters. Okay, and we'll do the calculations here. So if you do the calculations, 2 squared is 4, right? So we have 1/3 times pi times 4 times 1.5. And I'm going to kind of show you here how I can do this without even using a calculator, at least to start with here, if I want to write my answer in terms of pi. Because watch, 4 times 1.5. I mean, we all know that 15 times 4 is 60, right? So 1.5 times 4 would be 6. And 1/3 of 6 is 2. So we've got 2 pi meters cubed for the exact volume. Okay? So that would be the exact volume in terms of pi. But of course, in terms of practicality, we're not going to say that's how much the volume is going to be, you know, as far as if we were going to tell somebody how much corn we needed, right? So I'm going to convert that by multiplying by pi on the calculator. So using the pi button, you'll get a value a little bit more than 3.14. So a little bit more than 3.14 times 2 is a little bit more than 6.28. So the volume is going to be approximately 6.283, I'll squeeze that 3 in there, 6.283 cubic meters. Okay? So now, step 2, I need to convert meters cubed to tons. So I'm going to use the conversion factor that I was given here, that there are, highlighted in yellow here, that 1 cubic meter of corn weighs 0.8 tons. Okay, so let's use that. So step 2. Okay, we're going to convert meters cubed to tons. Okay, so we have 6.283 cubic meters, and we know that each cubic meter is 0.8 of a ton. Okay, so many of you would know to multiply, but if you weren't clear on that, let's show you why it works. Okay, so 0.8 tons per cubic meter, if we do the multiplication there and cancel diagonally, right? Because it's just like multiplying fractions horizontally. We can cancel the units diagonally, right? And then multiply horizontally. And when I multiply 6.283 times 0.8, I will get 5.0265 tons. And I'm going out a number of decimal places just so that at the very end I'm as accurate as possible. Okay, now finally, step 3. Okay, so step 3, we need to convert tons to loads. Okay, so let's look back up here at our information. It says that there are 1.75 tons of corn per load. Okay, So again, I can use a conversion factor here. Many of you would know to divide the number of tons by the number of tons per load. But just to show you what works, okay, and also to help you, because you'll be doing converting like this. You probably did it when you took physical science, but also when you go to chemistry, which many of you will be taking next year, you would be using a similar process here to convert units, okay? So we've got 5.0265 tons. And watch what happens. If I write one load per 1.75 tons, and I do the multiplication here, essentially what is really happening, I put, of course, tons over 1. If I multiply horizontally, I end up with 5.0265 tons in the numerator, or tons in the numerator, and I have, and then you can see the tons cancel, so 5.0265 in the numerator, and 1.75 in the denominator, just multiplying horizontally, which is basically what we talked about at the beginning here of this step. That it would make sense if you know the number of tons per load and you know the number of tons, you could divide the number of tons per load into the number of tons, and that'll give you the number of loads. Okay, so if I divide that, I get about 2.87, but you're not going to be able to get a fraction of a load in practical terms. So we'll just say that in order to be able to get what we need, we'll round that to about 3 loads. Okay? So that is an application problem, because I know, you all should be able to easily apply the formula to calculate the volume of a cone, but we want to be able to go farther than that and do a multi-step problem. Okay? And of course, always go back and pause and check and make sure you understand before you go on to the next. So let's look at the next example here. This time, as you'll notice, we have a triangular pyramid. You can see it's a triangular pyramid because the base here, which is this is the base right up here, the base is a triangle. Jason is using the mold to make 12 candles. Okay, so notice he's making 12 candles. How many cubic inches of wax does he need? Okay, so again, you have to think of this in 2 steps, because step 1, you need to know what the volume is for 1 candle, but then in step 2, you'll have to multiply by 12 because there are going to be 12 candles. Okay, so for step 1, let's find the volume of 1 candle. Okay, and I'll break this off so it keeps it separate. Okay, so step 1, let's find the volume of 1 candle. Okay, now for the volume of a triangular pyramid, we go back up here. We can see we're going to take the volume equals 1/3 the area of the base times the height. Okay, now of course this applies to any pyramid. The reason we don't see the formula for a triangle in for B is because I could have a square pyramid, in which case I'd be finding the area of the square for B, okay? So whichever type of pyramid you have, you'll find the area of the base, multiply that by the height, and divide it by 3, okay? So in this case, we have a base that's a triangle, so we have volume equals 1/3 area of the base times the height. Okay, now to get the area of the base, we're going to need 1/3, or excuse me, the area of the base is 1/2 of the area of the base of the triangle times the height. Okay, so I kind of went over this when I was shading in the base, but this 3 inches right here is the height of the triangle. Okay, and the 4 inches is the base of the triangle. Okay, so basically here you're just saying 1/2 of the base of the triangle, which is 4, times the height of the triangle, which is 3, and that is going to be substituted in for B. Okay, and you could calculate that over here. if you wanted to, or just do it all at once in the volume formula. I'm going to do it all at once because typically what most of you are going to do is you're going to do all the work in one equation anyway. Okay, so we've got 1/3. Now for the area of the base, and I'll highlight this so that you keep track of it. The area of the base is going to be what we've got from over here, and that's going to be the 1/2 of 4 times 3. Okay, and that's all this here. But then we also have this other h, and you have to be really careful because they're both lowercase h's, but they're different values. This lowercase h over here is the height of the pyramid. Okay, so in that case, the height of the pyramid here is 6. And so we'll multiply all this out. Okay, so I can kind of do this mentally. 1/2 of 4 is 2, times 3 is 6. 6 times 6 is 36, divided by 3 gives me 12. So the volume of one candle is 12 cubic inches. Okay. So that's the volume of one candle. And of course, very, very simply, step 2 is multiply by 12 to get the volume of 12 candles. So now we've got 12 times 12 equals 144 inches cubed for 12 candles. Okay. All right. So again, pause if you need to. Okay, so we're going to do a couple more problems, just applying volumes of pyramids. Okay. Diani is 1.8 meters tall and wants to be able to stand inside her tent. Should she buy this tent? Okay, so basically what we're trying to find out is the tent tall enough for Diani to stand in? So we look at the attributes that are described on the box. Okay, and if you look at the box, you can see it says 3.4 cubic meters for the volume. Okay, so you should be very clear. If you see cubic meters, you know that the volume is already given to you. Okay. The square floor, so basically here we have a square floor of the pyramid. Okay, so you have the square floor that is 8.4 meters in perimeter. So we know that the perimeter is equal to 8.4 meters. Okay. So to help us visualize this, I'm going to break out that square so you can see what information that we really have. Okay, so here's the square base. And we know that the perimeter is 8.4 meters. That means the distance around the square. So don't confuse that with the area of the square. So we know that the square has all 4 congruent sides. And given that all 4 sides are congruent, I can easily say that 8.4 divided by 4 means that each side is 2.1 meters. Okay? And I'm only labeling 2 of those sides because that's what you need to figure out the area. And remember that the volume of the pyramid is 1/3 the area of the base times the height. So I know the volume is 3.4 cubic meters. If I want to figure out how high the tent is, which is what I need to know to see if she'll fit in it, I have to solve for h. Okay, so I need to solve for h to see if the tent is tall enough. That's what I need to do. So this is, And the main part of the problem is one step. It's just that over here first, what you have to do is figure out what the area of the base is. So that's easy. The area of the base is the area of that square, which is 2.1 squared, or 2.1 times 2.1. And if I multiply that, 4.41 square meters is the area of the base. Okay? So I can go ahead and over here for B, I can say 4.41. And then I can solve for H, okay? So 1/3 of 4.41, if you work that out on your calculator, it's 4.41 divided by 3 is 1.47 times H. And then if I divide 3.4 by 1.47, I'll get that the height of the tent is 2.3 meters, okay? So Dayani is only 1.8 meters, which means that she has a whole 1/2 meter left there for her to be able to fit in that tent. So that means that yes, she should buy the tent. So since this is a type of problem you would want to write it out. So since the height of the tent is 2.3 meters, she can buy it because she is only 1.8 meters. Okay? So that would be the answer to this question. Okay? All right, so we have a little bit of a longer problem here where we're going to look at volumes of cones. Okay, now if you look at these drinks here, they are supposed to be smoothies. It says a restaurant sells smoothies in 2 sizes. Which size is a better deal? Okay, so we are approximating that these are cones, even though they're not obviously perfectly coned shape because you got the little curves and so on, but we're doing an approximation, right? And what we're given here is the diameter of the base in both cases. We see we have a large for $5.89 and a small for $3.49, okay? And to figure out which is the better deal, we need to find the cost per cubic centimeter in order to be able to figure out which one is the better deal, okay? And whichever one has a lower cost per cubic centimeter, that will be the better deal, okay? This is very similar to when you go to the grocery store and you need to figure out like which size item is a better deal. Perhaps you have a box of cereal in one size and a box of cereal in another size. And the tag in the grocery store, they pretty much will do the task for you. If you look carefully at the tags on the shelves, they'll give you the cost per ounce for one size box versus the cost per ounce of another size box. And it's not always true. Typically, the larger size is the better deal, but that's not always going to be true, okay? It depends, like if, for example, if there's a sale on the smaller size. But it's called unit cost or unit price, and that's what we're looking at here. So we're looking really at the unit price, okay? So basically, in order to do this, of course, step 1 is we're going to need to find the volume of each size drink, okay? And then, of course, once we do that, if we just divide by that or divide that into the cost, in other words, take the cost in dollars and divide that by the volume in cubic centimeters, we'll get the unit price, okay? So step 1, we're going to find the volume of each cone. Okay, and of course I said they're approximate cones. We're being approximate here. Okay, So we want to figure out the volume of the large size and then compare that to the volume of the small size. Okay, if I want, I can make like a little T-chart to keep myself organized. So then I have volume of the small over here. Okay, now in both cases, we're using 1/3 of pi r squared h to be able to figure out the volumes. Notice that we're given the diameters. So we need to recognize that, basically let's kind of recognize you've got a right triangle here. Okay, so we're given the diameter, which is 10 centimeters, but we know then that the radius is going to be 5 centimeters. Okay, and then similar to in the small size, we're given the diameter is 7 centimeters, and 7 divided by 2 is 3.5. So the radius is 3.5 centimeters. Okay? Now we need to be really, really careful here, because in both of these cases, we are given the slant height of the cone. And nowhere in this formula are we using slant height. If we were looking at surface area of cone, then we'd be using the slant height. But here, no, we need to know what the height is of each cone. So we need to think about how are we going to figure out what the height is of the cone. Okay, so think about that for a moment in order to be able to calculate the volume. You're given the hypotenuse of a right triangle and one of the legs, and it's very then easy to find the other leg, right? And hopefully you thought about it and you said, oh, I just need to use the Pythagorean theorem. Okay, so in both of these cases, before I can find the volume, I need to use the Pythagorean theorem to find h. Okay, so that we have to do first. So that's sort of within our step one. We have to find that. Okay, so looking at the triangle here, I've got that 5 squared plus h squared equals 15 squared. So 25 plus h squared equals 225. 225 minus 25 is 200. And if I take the square root, I will get the approximate height. Okay, now I'm going to try to be as accurate as possible in my final result. So, because I know I'm going to still have to calculate volume after this, and then I'm going to have to calculate unit price. So I want to go out several decimal places. So when I took the square root of 200, it's going to come out to a little over 14, because remember the square root of 225 is 15, right? So this is going to be a little under 15. It's actually 14.142 centimeters is that height. Okay, so I need to do the same thing for the small. Okay, and just to be different here, I'll write this, here I wrote 5 squared and then h squared. Here I'll write h squared and then 3.5 squared. It doesn't make any difference. Okay, equals 12 squared. And so if I work that out, I'm going to get h squared. 3.5 squared is 12.25. 12 squared, of course, is 144. If I subtract 144 minus 12.25, I will get 131.75. Take the square root, and we'll get that h is approximately 11.478 centimeters. And again, check yourself, does that make sense? The square root of 144 is 12. So if we have a little less than 144, we're going to have a little less than 12 for the square root. Okay? So now that we have the radius and we have the height, right? So we know that the radius here was 5 centimeters and the radius here was 3.5 centimeters. With the radius and the height, now we can find the volume, okay? So the volume is going to be 1/3 times pi times 5 squared times 14.142. okay? And working that out, 1/3 times 25. I mean, some of this I can kind of just do mentally, right? And then in my calculator, probably what I would do is multiply 14.142 times 25 times pi, and then divide by 3. Kind of like almost work it left to right here. Okay, because it's all multiplication. So honestly, you know, whether I worked left to right like the order of operation says or right to left, in this case it doesn't matter because it's all multiplication. It's all one type of operation. So when I multiply that out, I get 370.2 centimeters cubed, okay? And I just went out to the nearest tenth here. We only have one more operation to do, and that is to divide by or divide into the cost, okay, to be able to get the unit price. Okay, so before I do that, I'll find the volume of the small as well. See, it's useful here when you're doing a problem like this where you have to do two examples basically following the same steps. You might as well do them in parallel, do them at the same time, and then, you know, it kind of keeps everything organized. Okay, so I've got 3.5 squared here for the radius squared, and then the height is 11.478. And I'm going to multiply that out, and I've got 12.25 here. You might want to do that ahead of time before you do everything else. Then multiply in the same manner I did over here, and I'll have approximately 147.2 cubic centimeters. Okay? So now, step 2, now that I've got the volume, I need to take the cost and divide it by the volume to get the unit price, to figure out which size is a better deal. Okay? So, step 2 is to find the unit price of each size, which is the cost per centimeter cubed. Okay? So again, so the unit price of each size, again, if I want, I can make a T-chart to help me out. So this is the large and this is the small. Okay? And so I'm basically going to say for the large, if you look back up at the picture, it's $5.89. So we're going to say $5.89 divided by 370.2 cubic centimeters. And if you divide that out, you get in dollars 0.016 per centimeter cubed. Okay, think about that. Basically, you're talking about here between a little over 1.5 cents. That's what you need to understand, right? Because if I cover up the 6 there, 0.01 is 1 cent, and this is 0.016, so that's a little over 1.5 cents per cubic centimeter. Okay, now if we go over to the small, we're going to say $3.49 divided by 147.2 cubic centimeters. And dividing that out, we get 0.024 per centimeter cubed. In other words, a little under 2.5 cents, right? Here's 2 cents, so a little under 2.5 cents per cubic centimeter. So clearly the small is slightly more expensive, okay? So officially, of course, the large is a better deal, okay? But in practical terms, you know, so that's what our mathematical answer is, of course. You know, we're going to say that the large is a better deal. That would be the correct answer to this question, right? Now, in practical terms, we all know if we actually are going to that smoothie shop, if we know we're not going to drink a whole large, it makes more sense to get the small because really the price difference isn't all that much. Okay? All right. So we're going to do just a couple of more questions here dealing with pyramids and cones. And then I definitely would suggest that you pause before you go on to section 11.4 on spheres. Okay, so you'll notice this is the try it section. Okay, you definitely might want to even pause at this point and try these next couple of questions on your own and then check your answers with me. And that will be a good test to see if you're ready to go on to do the topic 11.3 assignment in Pearson Realize. Okay, and you may even want to do that topic 11.3 assignment in Pearson Realize before you go on to listen to the rest of the video on section 11.4. Get the Pearson Realize 11.3 done first, and then go on, watch the video for the rest of the video on 11.4 and do that assignment, okay? That way it breaks it up and keeps it fresh in your mind, okay? All right, so perhaps you paused, perhaps not. A cone has volume of 144 pi and a height of 12. What is the radius of the base? Okay, so first of all, we know this is a cone, so we know we're going to use the formula 1/3 pi r squared h. Okay, and I know the volume is 144 pi. And what we're looking for is the radius, so we're working backwards here. We know what the height is, we know what the volume is, and we're looking for the radius. So we've got 1/3 times pi times r squared times the height, which is 12. Okay, you notice they're not giving us units here, so we're just saying, you know, in some random generic unit. Okay, so let's multiply this out. And I want you to notice, this is really, really important. If we're solving for r here, we have pi on both sides of the equation. So it is definitely not efficient to put pi into your calculator, because if you divide both sides by pi, pi will cancel out. So let's just go ahead immediately and cancel pi out and make the equation a lot simpler. Okay, so now I have 144 equals 1/3 of r squared times 12. Okay, and then again, mentally, without using a calculator, I know that 1/3 of 12 is 4, because 12 divided by 3 is 4. So I've got 144 is equal to 4r squared. Then divide by 4 on both sides, so we get 36 equals r squared. And of course, then to get r, we just take the square root. And remember, this is really important, especially going into Algebra 2 soon, that when you solve an equation, quadratic equation, this is quadratic because there's a square in it here, okay? So at this point, it's a quadratic equation anyway. And when you solve a quadratic equation, we take the square root, you're going to get a plus or minus in your answer. But I'm not going to take plus or minus here because I know that a length can't be negative, a radius can't be negative. So the square root of 36 that's positive is going to be 6. So I know that the radius is going to be 6 units. Okay, there's my answer for part A. Now, question for part B. If the radius of the cone is tripled, what is the new volume? Second question, what is the relationship between the volumes of the two cones? Okay, so it says if the radius of the cone is tripled. Well, we know the radius is 6. So tripling it means that the radius of the new cone is going to be 18 units. Okay, so, you know, the simplest way to do this, of course, for many of you might be, okay, well, now I know what the radius is. I know the height is still 12. I can just substitute those into the formula and find the new volume, right? And so many of you might think that's the simplest, okay? But let's just make a prediction here, Okay, let's just go off to the side and predict what's going to actually happen. We'll actually calculate that to verify it. But I want you to notice something here. Okay, basically, if we consider r the original radius, and we're saying that we're tripling it, okay, you notice that whatever the r is here is being squared. So if I triple the radius, and then in order to find the volume, I'll have to square it. Let's see what happens to the original value of r. If you go back to basic algebra skills, if you square this product, you have to square each factor, okay? So 3 squared is 9, r squared. And you see r squared in that formula. So essentially, you'll notice what's happening here is that you're going to really be multiplying the volume by 9 because that tripling factor 3 is actually being squared in the formula. Okay? And you might remember from when we studied similar figures a while ago that if we looked at the length of a square, for example, and we looked at the length of a square that was similar to it, right? If I triple the length of the square, I'm actually going to be multiplying the area by 9 because that length is squared when you find the area, okay? Same is true with volume. Like if we had a cube, if I knew the length of the side of the square was a certain length, to find the ratio of the volumes of similar cubes, I would actually cube that length, the ratio of the length of the sides, okay? So basically here, in answer to the question, if the radius of the cone is tripled, what's the new volume? You'd be taking the volume and you'd be multiplying it by 9. So 144 pi times 9, so the new volume, 144 times 9, would be 1,296 pi cubic units, okay? So let's see by actually doing that if it works. Let's check it. Let's actually calculate the volume using a radius of 18, because that would be the triple of the radius of 6. So let's check that out. So the volume of the new cone would be 1/3 times pi times the new radius, which is 18, squaring that, times the same height, which is 12, okay? If I multiply that out, 18 squared is 324 times 12. So if I multiply 324 times 18, excuse me, divide by 3, I will get 1,296 pi units cubed, just like I predicted, okay? So what I'm saying here is what we did over here is really the shortcut, okay? If you can follow that, if you understand that we squared 3 to get 9, you're really taking the volume and multiplying it by 9 when you're multiplying the radius by 3, okay? This is the new volume. So what's the relationship between the volume of the two cones? The volume of the new cone is 9 times that of the old cone. That's the answer to that second part, okay? So there's basically 2 questions here. You answered one here and the second part here, okay? All right, last question in section 11, topic 11.3 from Pearson. A cone-shaped hole is drilled in a prism. The height of the triangular base is 12 centimeters. What is the volume of the remaining figure round to the nearest tenth? So we're calculating remaining volume here, okay? Originally, we have a triangular prism. And when they're talking about the height of the triangular base, okay, you have a triangular base here, of course, and of course, up here, we have a triangular base as well, right? That's parallel to it because it's a prism. And we understand that what we're doing here is we're going to calculate the volume of the prism, and we're going to take away the volume of the cone. Okay, so the volume remaining is going to be equal to the volume of the triangular prism minus the volume of the cone. Okay, because you're basically cutting that cone out. Okay, now to find the volume of the triangular prism, first of all, focus on the fact that it's a prism. So the volume of the prism is not with a factor of 1/3. It's just the area of the base times the height. Okay, so that's what we learned back in one of the last two sections in topic 11.2. Okay, so that's the volume of the prism is the area of the base times the height with no 1/3 there. Okay, the volume of the cone is 1/3 area of the base times the height, but of course the base is a circle, so that's 1/3 pi r squared h. Okay, so when you're calculating the volume of the triangular prism, you want to recognize the information they gave us here. The height of the triangular base is 12 centimeters. So that means that this height right here on the flat surface, okay, in other words, you've got a triangle here, that is the base. Here's the triangular base. And that height here is 12 centimeters. Okay, so you want to be really, really careful and don't confuse that with the height of the prism. Okay, the height of the prism is 8 centimeters. That's this height here. Okay, but also realize that's also the height of the cone, because the cone and the prism share the same height, because that cone is, you might not be able to tell from the drawing, but that vertex of the cone is touching the base. Okay, so that 8 centimeters we're going to use for the height of the prism and also for the height of the cone, while the height of the triangle is 12 centimeters. The base of the triangle is 22 centimeters. Okay, so when we're trying to calculate the area of the base here for the triangular prism, we're saying 1/2 of the little b times the h, that is the height of the triangle on the base. So we've got 1/2 of the base times the height. So 1/2 of 22 times 12. Okay, and I'm going to highlight so we understand where this is coming from here. Okay, that's this area. While the height here, h is the height of the prism, which is 8 centimeters. Okay, that's this value. Okay, and we'll subtract the volume of the cone. So we have 1/3 times pi. The radius of the cone is 3 centimeters. And the height of the cone is the same as the height of the prism, 8 centimeters. Okay? So we're going to go ahead and we'll multiply this out. So we've got 1/2 of 22 is 11. 11 times 12 is 132. And 132 times 8 is going to be 1,056. Okay? I'm going to subtract out 1/3 of pi times 9 times 8. And if I multiply that out, I get 75.398. Okay, and if I subtract 1,056 minus 75.398, I will get, it says round to the nearest tenth. On my calculator, I got 980.602, so I'm just going to say 980.6, And think about the units, okay? The units are in cubic centimeters because this is volume. So 980.6 cubic centimeters. Okay, so at this point, I would definitely pause because you'll notice the next page we're on to volumes and surface area of spheres. So you definitely want to take a break before you continue. Okay, so we're going to continue now. We just finished up volumes of pyramids and cones, and we're going to go on now to volumes and surface area of spheres in section 11.4. Okay, so we're going to look first of all at what the formulas are for surface area and volume of a sphere, which you've probably seen before in middle school, but we're going to look at them in a little bit more depth here, apply them, and I'll even give you a little bit of a hint of what other formulas that we've learned that they are related to, so therefore where the formulas come from, okay? So the surface area of a sphere. Okay, so we're basically talking about a ball, all right? And when we're talking about a ball, the surface area is the part of the ball that we're touching, right? And the volume is the space inside the ball. So of course, the surface area is in square units where the volume, the space inside, is in cubic units, okay? So let's look for a moment at the surface area and look at where that comes from. Okay. The volume, or excuse me, I should say the surface area of a sphere, the surface area of a ball, is going to be the same as the lateral surface of a cylinder. Okay, so actually I'm going to pause a second. I'm going to go grab a label. Okay, so I have this label from a soup can. And if you remember when we were looking at surface area of cylinders, we said that the lateral surface of a cylinder, the side of the cylinder, not the bases, not the circular top and bottom, but the lateral surface of a cylinder is a rectangular shape. And I can tell because if I take the label off the surface, of course, it is a rectangle, okay, that has its length as the circumference of the can and its height the same as the height of the can, right? So what we're saying here in terms of spheres is that the surface area of a sphere, if it has the same radius as the radius of a certain cylinder, that the surface area of the sphere, the area that I can touch on that sphere, on that ball, is going to be the same area as the lateral surface of the cylinder with the same radius. So you basically what I'm saying is if I actually had a ball that had the same radius of this can, I could wrap this paper around the ball and cover it, okay? So we can kind of see formula-wise how that works then. So you'll notice here that if I were to take a cylinder, okay, and let's pretend, you know, obviously I didn't draw it to scale here, but let's say that this R is the same length as this R on this ball, okay? We know from our study of surface area of cylinders that the lateral area of the cylinder is equal to 2 pi r h, right? The circumference of the can is the length of that rectangle times the height, okay? Now, if I draw this, and again, this is not to scale, but if I draw this cylinder with a height that's 2r, that would be another requirement here for this to work. If the height is twice the length of the radius, and the radius is the same as the radius of the sphere, then this lateral area is going to be the same as the surface area of the sphere. And so watch, 2 pi RH, let's work this out, okay? 2 pi r, I'm going to let h equal 2r. I'm going to multiply this out. 2 times 2 is 4 times pi. R times r is r squared. Sure enough, check it out. They match, okay? So that's where this formula comes from. It comes from the lateral area of a cylinder with the same radius and the height double that radius, okay? All right, so we're going to do an example here, and this example is going to help us see where the volume formula of a sphere comes from, okay? So we're going to do a little bit of review here also. We're going to calculate the volumes of these 3 solids, okay? And I'll make a table here. Now this solid is half of a sphere. It's called a hemisphere, okay? So this is a hemisphere with a radius, and I'll say half here, right? Hemi half. Half of a sphere, and the radius here is 10 meters, okay? And we have here a cylinder with a radius of 10 meters and also a height, that same value of 10 meters. And finally, we have a cone with a radius of 10 meters and a height of 10 meters, okay? So let's calculate the volumes here. So first of all, the volume of a hemisphere. So let's use the formula that we have right up here. This is the volume of a sphere, okay? So I have half a sphere here. So let's check this out. I've got the volume of the sphere was 4/3 pi r cubed, right? But I want the volume of a hemisphere. I want half the sphere, okay? So that's going to be 1/2 of 4/3 pi r cubed, okay? So we'll take 1/2 of that. Now let's just do some canceling here. 2 goes into 4 2 times, canceling diagonally, multiplying horizontally. That tells us that the volume of a hemisphere is going to be 2/3 pi r cubed, which makes sense, right? Half of 4/3 is 2/3. So this is a formula actually that'll be really useful to you to use. Also, the formula for a volume of a hemisphere is 2/3 pi r cubed, okay? So if we calculate that out, we'll say 2/3 times pi times 10 cubed, right? Now we know 10 cubed is 1,000, times 2 is 2,000, divided by 3 is going to be 666 and 2/3 pi. So I'll just put a 6 with a bar over it, pi meters cubed. Okay, I'm going to leave it in terms of pi because it'll be easier to make the point that I'm going to make at the end about the relationship between these 3 figures. Okay, now let's look at the volume of a cylinder. Okay, we know the volume of the cylinder is the area of the base times the height, which is pi r squared times h, because the base, of course, is always going to be a circle, pi r squared. So we've got pi times the radius, which is 10 squared, times the height, which is 10. So this is really just 10 cubed, right? Which is 1,000. 1,000 times pi. So the volume of the cylinder is equal to 1,000 pi cubic meters. Okay? Now, let's look at the volume of the cone. Now, we know that when you're looking at a cylinder and a cone that have the same radius and the same height, the volume of the cone is going to be 1/3 that the volume of the cylinder. So I should come out to 1,000 divided by 3, or 333 1/3 pi cubic meters. But I will verify that. We'll work from scratch, and you'll see that it works. So we have 1/3 area of the base times the height. So we have 1/3 of pi r squared h, or 1/3 of basically the expression we had here. Pi times 10 squared times 10. And sure enough, we have the same, basically a third of 1,000 pi, right? Or 333.3 pi meters cubed. Okay? Now I want you to look at these three numbers for a moment and think about doing some subtraction. And think about, what could I subtract from what to get what? Think about that for a moment. Maybe pause before I tell you. Okay? So this is what you should have thought of if perhaps you paused, is this. Watch. The volume of the hemisphere equals the volume of the cylinder minus the volume of the cone, of course, assuming they all have the same radius and the cylinder and the cone have the same height and it's the same as the radius of all three. Okay? Watch. If I take the volume of the cylinder, which is 1,000 pi, and subtract the volume of the cone, which is 333.3, repeating, pi, sure enough, I get the volume of the hemisphere, which is 666.6 pi, repeating. Okay? So basically, that's where the formula of a sphere comes from. For the volume of a sphere comes from. Okay, so basically you can see if I take the difference between the volume of the cylinder and the volume of the cone, and then that'll give me the volume of the hemisphere. If I double that, I would get the volume of the corresponding sphere, again with the same radius and of course the heights being the same as that radius. Okay, so we can see that's where we get the formula for the volume of a sphere. Okay, so we're going to do just a couple more examples here, and then we'll be done with this lesson and with this video. Okay, so we're going to use the volumes of spheres to solve problems. And basically, let's read this question and you'll notice the drama club makes a big ball from foam to hang above the stage for a play. Okay, so here's the ball, which is obviously the big ball is a sphere. Okay, they plan to cover the surface of the ball with metallic fabric. So really, although we're heading this volume of spheres to solve problems, we're interested also in the surface area. They plan to cover the surface of the ball. So use the volumes of spheres to solve problems, including surface area. Okay, so what's the minimum number of square meters of fabric that the club needs? So we're really, in the end, what we're looking for is we need to calculate the surface area. And if you look at what you're given here, you're given the volume. Okay? So you have to think about, how can I use the volume to find the surface area? And what that comes from is basically thinking about what is the relationship between these formulas. Volume is 4/3 pi r cubed. Surface area of the sphere is 4 pi r squared. And so think about, what do these two formulas have in common? What variable do they have in common? And hopefully you would notice they have r in common. So our strategy here is to use the volume to solve for r, and then once we get r, we can substitute that into the formula for surface area to find the surface area. Okay, so step 1 is to use the volume of the ball to solve for the radius. Okay, and then step 2, use the radius to calculate the surface area. Okay, so we've got volume equals 4/3 pi r cubed. Okay, so the volume is 1.8 meters cubed equals 4/3 times pi times r cubed. Okay, so we have to use our algebra skills to think about how to solve this equation. Okay, notice in this particular situation, we have pi only on one side. Okay, and actually I'm going to get rid of the meters cubed here. I'll just leave this as 1.8 on this side. Make it easier. We don't need the units within the equation. Okay, so that's just 1.8. So what you want to notice here is that pi is only on one side of the equation, so I'm not going to be able to cancel out pi, okay? But what I need to do is I need to isolate r, which really means that I need to isolate the factor r cubed and then take the cube root, which is the opposite of cubing, to get r. So I'm going to need to divide by both pi and by 4/3 to get r cubed by itself. Okay, now hopefully you remember from algebra, when you have a fraction, rather than dividing by 4/3, it makes more sense to multiply by its reciprocal, 3/4, right? It's like keep, change, flip when you divide fractions. So I'm going to multiply both sides of the equation by 3/4 to cancel out the 4/3. So 3/4 times 1.8 equals 3/4 times 4/3 times pi times r cubed. Okay? So the 4's are going to cancel and the 3's are going to cancel. And now if I multiply 3/4 times 1.8, you can do that in your calculator, 3 times 1.8 divided by 4 will give you 1.35 equals pi r cubed. Okay. Now, to get r cubed by itself, of course, you're going to need to divide by pi. So we're going to divide both sides by pi. And you can do that in your calculator. And when you divide by pi, let's go ahead and do this in our calculator together, because we're going to have to learn how to use cube root on the calculator too if you're not familiar with that. Okay, so I'm going to say 1.35 divided by pi, here's the pi button, equals, because you can see the pi written across, so make sure you hit equals. Okay, so you're going to get 0.4297. Okay, so I've got 0.4297 equals r cubed. Okay, Now, to be able to get R, I have to take the cube root. Okay? In other words, I'm going to take the opposite of squaring is square root, the opposite of cubing is cube root. Okay? So this is a 3 right here. I know it's kind of small. So I've got R cubed there, and I rewrite that so it's a little bit clearer for you. So I have R cubed, okay? And I'm going to take the cube root of both sides, right? So there's like a little 3 there inside that radical for the index. So I'm taking the cube root of both sides. So to do that on my calculator, cube root is the second function right above the 0. I'll zoom in on that for you. Okay, and so if you have your own calculators there with you, you can use them. And if you just hit second 0 now, you'll get the cube root. Okay, so you see this in your calculator, you just hit second and then 0. And you don't even have to hit equals there, it gives you your result. Approximately 0.75. And it didn't say what to round to, so I'm just going to say about 0.75 or 3/4 of a square meter. Okay, so basically the R here, or I should say 3/4 of a meter. So we've got R is approximately 3/4 of a meter, and actually, since I'm going to plug it into the next part, I'll go out 4 decimal places, so we'll say 0.7546. Okay, so 0.7546 meters is going to be the radius. Okay, so I will use that now in order to be able to calculate the surface area. Okay, so we've got the radius. Remember, that was what was in common between the volume and the surface area formulas. So now I can calculate the surface area. So surface area equals 4 pi r squared. So I've got 4 times pi times 0.7546 squared. Okay, and you can all work that out on your calculators. If you work that out, you'll get approximately 0.7546. Make sure you square that first, then multiply by pi, then by 4. Okay, so you'll get approximately 7.156, and I'll round to the nearest tenth, so about 7.2 square meters of fabric for the surface of the ball. Okay. All right, last question. We're going to use the volumes of composite figures, okay? So remember when we were looking at area of figures, we had composite figures where we put together, for example, a circle or a half circle with a square or triangle, and we calculated the total area by adding up the areas. We're going to do the same thing here with volume, okay? So you notice here what we have is we have a cylinder, and up here we have a hemisphere. Okay, and what we're going to do is we want to add them together to get the total volume. Okay, so we've got a solid is composed of a right cylinder. Remember, it's called a right cylinder because basically you can see here is the height, and we know that the height here is going to be perpendicular to the base. So this is as opposed to an oblique cylinder where you'd have that slanted cylinder. Okay, so it's composed of a right cylinder and a hemisphere, a half of a sphere as shown. If the density of the solid is 100 kilograms per cubic meter, what's the mass of the solid? Okay, so we're given the density in mass per unit volume. Okay, so we've got 100 kilograms per cubic meter. And obviously here, what we don't know is the volume. Okay, if I know what the volume is, then I can take the density and multiply it by the volume, and I can figure out what the mass is of the entire solid, because for each cubic meter, I've got 100 kilograms. If I know how many cubic meters there are altogether and I multiply it by 100, I will get the entire mass of the composite figure. Okay? So step 1, we want to find the volume. Okay? So the volume of the composite figure is the volume of the cylinder plus the volume of the hemisphere. Okay? So the volume of the cylinder is, of course, pi r squared h, the area of the base, times the height. The volume of the hemisphere, remember we came up with the formula taking half of the volume of a sphere, right? Half of 4/3 was 2/3. So we have 2/3 of pi r cubed. Okay? Now, what's the radius here for both of these? Well, the diameter is 2 meters, so the radius is half of that, right? So the radius is going to be 1 meter. Okay? The height of the cylinder is 3 meters. So this is very simple to substitute. So I've got pi times 1 squared times the height of 3 plus 2/3 pi times 1 cubed. Okay? So these numbers are relatively easy to work with because 1 squared is 1 times 3 is 3. So this is 3 pi plus 1 cubed is also 1, right? 1 times 1 times 1 is 1 times 2/3 is 2/3. It makes the most sense to just add these two together, combine like terms, and then multiply by pi. Okay? So 3 plus 2/3 is going to be 3 2/3 times pi. 3 2/3 pi, or 3 times 3 is 9, plus 2 is 11/3 pi cubic meters. Okay, so that's the volume. Now, to be able to find the final answer, which is what is the mass, that's step 2, right? So we're going to multiply to find the mass of the composite figure, because we know the density is 100 kilograms per cubic meter times, if we work this out, now we have 11/3 pi meters cubed. So what we might want to do here is let's go ahead, before we multiply it, let's go ahead and figure out what this mass is, or this volume is, after we've multiplied by pi. Now, if I multiply by pi, I'm just going to kind of approximate that and just say, if you multiply 11/3 times pi, it comes out to about 11.5 cubic meters. Okay, so 100 kilograms per meter cubed times 11.5 meters cubed. Multiplying that out, of course, meters cubed cancel. 100 times 11.5, hopefully you can even do this mentally. Move the decimal 2 places to the right and you'll get 1150 kilograms. And that is the mass of the composite figure. Okay. All right, so go back through this video if you need to. If you didn't pause, go back, look back at information that you might need. And now you should be all set to be able to do topic 11.4 Pearson Realize. If you haven't already done the topic 11.3 Pearson Realize, you should be ready for that now as well. Okay, have a good day.